Hi folks, I'm Mr. Fullerton, and today I want to talk to you about conservation of energy. Our goal today is going to be to apply conservation of energy to analyze energy transitions and transformations in the system, and we'll use this to solve a variety of different types of problems. So to begin with, you've probably heard the law of conservation of energy before. It says something like energy can't be created or destroyed, it can only be changed. Well, that's true for the most part. When we get into the nitty-gritty of things, we find that mass and energy are very closely related, but mass is a highly concentrated form of energy. So really this should say mass energy cannot be created or destroyed. But conversions of mass into energy are fairly rare in terms of the problems we're going to be dealing with in this unit. So we can say that mechanical energy is conserved. That means the kinetic energy plus the gravitational potential energy plus the potential energy from a spring is constant. Now, if there's friction, we also have internal energy, but in the absence of friction, mechanical energy is going to be conserved. So we have conservation laws that total energy or mass energy is always conserved, not created or destroyed, and if we neglect friction, mechanical energy is conserved. Let's see how this can be applied. If we start with the problem of an FA-18 Hornet with a mass of 20,000 kilograms coasting through the sky at an altitude of 10,000 meters with a velocity of 250 meters per second, we can find its total energy. Its total energy is going to be equal to its potential energy due to its height above the surface of the Earth, or gravitational potential energy, plus its kinetic energy. That's going to be mgh plus 1/2 mv squared. When I substitute in with units, I have a mass of 20,000 kilograms. I have g, the acceleration due to gravity, of 9.8 meters per second squared, and its altitude of 10,000 meters, plus the kinetic energy portion, 1/2,000 kilograms, times the square of its velocity, 250 meters per second, squared. And when I put all that together, I find that the total energy comes out to be about 2.59 times 10 to the 9 joules. A very large amount of energy because you've got a high velocity, a high altitude, and a pretty big mass. Now, if we take this a bit further, this FA-18 dives to an altitude of 2,000 meters. Let's find the new velocity of the jet. Well, the total energy is now going to be potential energy due to gravity plus kinetic energy, which is going to be mgh plus 1/2 mv squared again. If we're looking for its velocity at the new altitude, though, we can solve for velocity by saying 1/2 mv squared equals the total energy minus mgh, or getting v by itself, velocity is going to be equal to 2 times the total energy minus mgh, all divided by the mass, and we take the square root of that whole thing. Now when we substitute in with values, have to remember that total energy we found in the previous problem, 2.59 times 10 to the 9 joules. It doesn't change because energy is conserved, minus mgh, 20,000 kilograms, times g, 9.8 meters per second squared, times our new height, 2,000 meters, all divided by our mass of 20,000 kilograms, and we have to take the square root of that whole thing. When I do that, I come up with the velocity of 469 meters per second. So what really happened is the jet traded in altitude for velocity, which is why conservation of energy is such an important concept for fighter pilots. Oftentimes they need to make trade-offs between altitude and velocity, and they even consider their altitude as another form of energy. So being a good fighter pilot is all about conservation of energy and understanding these energy transformations. Let's say we drop an object from a height of 10 meters. We already know how to solve for the velocity of that object right before it hits the ground using kinematics, but we could do the same thing with an energy approach as well. Let's try it both ways and see what happens. From an energy approach, we know that the total energy at the top must equal the energy at the bottom, assuming we neglect friction, because energy is conserved, conservation of mechanical energy. Well, that means the potential energy due to gravity at the top must be equal to the kinetic energy at the bottom.
So mg times the height at the top must equal 1/2 m velocity at the bottom squared. Or if I solve for velocity at the bottom, that's going to be square root of 2gh. Or when I substitute in with values, that's going to be 2 times 9.8 meters per second squared times our height of 10 meters, square root of all of that. So the velocity at the bottom comes out to be square root 2 times 9.8 times 10 is about 14 meters per second. Let's see if we can't solve for the same thing using our kinematics. If we use kinematics, we would start off with our kinematics table, V initial, V final, our displacement, d, or in this case delta y, our acceleration, and time. Initial velocity for something dropped is going to be 0. The displacement in the y direction is going to be 10 meters, assuming we call down positive. The acceleration will be 9.8 meters, and we want to know the final velocity, v. Well, we can use the formula v squared equals v initial squared plus 2ad. That's going to be 0 squared plus 2 times 9.8 meters per second squared times 10 meters. If I have v squared, I take the square root of both sides to find v, and I come up with the velocity of about 14 meters per second. Who'd have guessed we get the same answer either way? Kinematics or our energy approach, conservation of energy. And of course, we should get the same answer. A couple different ways to solve the same sort of problem. Here we have a lawyer who knocks her folder of mass m off of her desk of height h. What is the speed of the folder upon striking the floor? Well, the folder's initial gravitational energy becomes its kinetic energy right before it strikes the floor. So the potential energy of the object when it's on the desk must equal the kinetic energy right before it hits the floor. Or mg times the height of the desk must equal 1/2 mv squared. And notice that the m's make a ratio of 1 and cancel out, so that when we solve for v, we find that the velocity right before it hits the floor is the square root of 2gh. Assuming we neglect friction, when you drop an object from some height, you'll find that its velocity right before it hits the ground is always going to be square root of 2gh. So you'll see that formula come up again and again and again in physics. The work done in accelerating an object along a frictionless horizontal surface is equal to the change in the object's work done is equal to the change in the object's what? Well, when you do work on an object, you give it energy. That's the work energy theorem. And if it's on a horizontal surface, what type of energy do you give it? You can't change its gravitational potential energy because you're only moving it horizontally. So you must be giving it kinetic energy.